Everybody have a copy of the notes? All right. Looking into the future, besides the project that you've just given me, you've got homework 13 due on Tuesday, and that's the application of these gradually varying flow methods that we've covered the last few lectures, culminating with today's lecture on the standard step method. And that's what those problems are that you've got, is one of each of the methods, except for standard step, you've actually got two problems. Our final exam is scheduled for Tuesday, the 6th of May at 2:45 p.m. And as I've mentioned previously, that exam is going to be comprehensive, but there will be emphasis on the material covered since the first exam. Since the exam 2. So it's not practical for it to not be comprehensive. For example, you have to know how to calculate the normal depth and the critical depth to solve a water surface problem. So I couldn't give you something strictly that excludes material since during the first and second midterm exam, but I'll try to focus the point value on new information since you've been tested last. I'll provide an equation sheet for the exam, and in fact I'll give you that equation sheet next week so that you can begin looking at it and familiarizing yourself with what the equations are, when they should be used and when they shouldn't be used, and so on. You can use Excel during the exam, and in fact it'll be encouraged because I will give you a water surface profile problem. I'm not going to tell you in advance whether it'll be numerical integration, direct step, or standard step. But you will need to use one of those methods, and Excel sure makes it a lot easier to do that. So that's all I've got to say about the final exam for today. We'll have some additional information next week when I give you the equation sheet. No, you won't do that. All right, so the standard step method is more sophisticated but more complicated than either of the two techniques that we've used before. Last time when we were working with the step-by-step method, as it's sometimes called, or the direct step method more commonly, you can only use that approach when the section upstream and the section downstream have the same shape. So if it's rectangular upstream and downstream, and you can use the direct step method, but the standard step method has flexibility built in for a change in shape. And of course that's going to be important in the real world because river cross-sectional widths are always varying from place to place. And even in engineered structures there are often transitions in width and shape and profile. And so we need to have a method that allows us that flexibility, even if it is a little bit more complicated to solve. The standard step method is that approach that allows us to calculate what is some unknown depth upstream, or how far is the distance to a depth that we're interested in upstream or downstream, depending on whether it's supercritical or subcritical. And so it's shape independent, and that's the approach that's built into HEC-RAS, because HEC-RAS does allow you to consider channels where the cross-sectional shape is varying. And so there is a bit of new terminology that's going to be introduced. And let's look at, first of all, just a diagram. And contrary to everything else we've seen for the rest of the semester and last semester, you'll notice that here 2 is upstream and 1 is downstream. And so that's something new. And just to emphasize that we've got a change in the notation, I'm putting a little siren there, the warning light, that 1 means known and 2 means unknown. It doesn't mean upstream versus downstream, as is commonly the case. So in the standard step method, the location where you know the depth is what you're going to assign as location 1. And the location upstream or downstream where you don't know the depth is going to be location 2. And so as it mentions here, if you've got subcritical flow, then the known section will be downstream. So we've got subcritical flow here, and section 1 is the downstream location, section 2 is upstream. When you have supercritical flow, the convention is to work from upstream towards downstream. And so in the case of supercritical flow, location 1 would be upstream, but it's not because it's upstream, it's because it's the known section. The computational approach is for us to calculate the water surface, and WS, or water surface, is the sum of the elevation above the datum and the depth. And so in the approach that we're going to be working with, one of your columns will be the water surface at 1 and the water surface at 2. And you can think of it as like an elevation to the water surface. Rather than just the depth, we've got some datum, maybe sea level is the datum, or there are other datums out there. We're just going to have the elevation of the water relative to some datum that we're going to be measuring. We also take into account the velocity head to take us up to the total energy line, and we're accounting for head loss. And so it seems strange to see head loss over on the left-hand side of the equation. We're not accustomed to seeing head loss on the left side of the equation. Usually head loss is over on the right side of the equation, and the reason why we ordinarily see it on the right side of the equation is that normally we don't have a flipped upstream and downstream notation like we do here. So what this is saying is that you've got some energy at 2, and the energy at 1 is the same as the energy at 2, but you have to account for how much energy is lost between the two. And so WS1 plus the velocity head is going to be less than the amount of energy there was at 2 by the amount of the head loss. And the head loss, of course, is equal to the slope of the energy grade line multiplied by the length between the two sections. Okay, so here's the head loss depicted graphically. This is a total energy balance rather than a balance on specific energy. Specific energy balance, remember, is when we're measuring energy above the channel bottom, but here we're measuring energy relative to a datum that's the same for both location 1 and location 2. So here's the method. And Andrew asked a question earlier about whether I'm going to allow you to customize the equation sheet in the exam, and the answer is no. I won't allow you to write down what the column headings are for spreadsheet problems, but I will present the equations in the order that you need to use them. And so that'll sort of guide you in how to solve the problem. The equations will be presented in this order on the equation sheet for the exam. The process that you go through is, first of all, you're not going to know what the depth is at the unknown location. At 2, you don't know the depth, and so you have to make an assumption. And so you'll assume some depth. And oftentimes it's a fine assumption just to say, I'm going to assume the water depth at 2 is the same as the water depth at 1. Sometimes you run into trouble with that and the solution won't converge. And so if you're going through this process and you just can't get a reasonable answer, it might be that your guess value of the depth at 2 needs to be modified. But ordinarily you'll get away with just letting it equal the depth at 1 just fine. Then, based on this guess of the depth, you have to calculate how much head loss would there be between 1 and 2. And then, also based on this guess of what the depth is, you need to calculate what would the head loss be based on the slope of the energy grade line at the midpoint. So remember, S sub F bar is saying what's the energy grade line slope at the midpoint between the two sections. You calculate that using Manning's equation, rearranged to solve for the slope. So here is Manning's equations, solved to rearrange for the slope. And then this term, C times the absolute difference in the velocity heads, this is a factor. The C factor accounts for the change in shape, because this might be a channel that's getting wider, or it might be a trapezoid leaning up into a rectangle. And anytime you have a change in shape, you have to account not just in the friction losses, but also you have to account for the transitional losses, which previously I've said are somewhat analogous to like local losses. If you have a changing shape, there will be some C value that's related to that energy loss due to turbulence induced by the change in shape. So S sub F times L, that's friction losses. And then I won't call it local losses here, but it's similar to it because it's a result of some change in shape. And then what you need to do is compare these two. You're comparing a calculated and an observed energy loss. The observed energy loss was based on a guess of the depth. the calculated energy loss is based on kind of an alternate view of that depth. It's based on what are the energy implications of that guess based on Manning's equation. And if they don't match, if they're not exactly the same, that tells you your guess isn't right. And so you can calculate an updated water surface depth according to this formula. You use your previous, initial guess of the water surface depth and the adjusted water surface depth to come up with an updated one, and then you start over again. You iterate this process from the beginning. Instead of just with a blindly assumed water surface, you use this updated water surface as your initial assumption in the next iteration. So in class on Tuesday, we had different rows on the spreadsheet. And what did each one of those different rows represent? Why did we have multiple rows? What were we breaking up into pieces? The water surface curve, right. So remember, we had lots of rows in our spreadsheet because we had a curve that we didn't want to approximate as a line. We wanted to approximate as a series of little lines, segments that together would better approximate the shape of that curve. So that's why we had different rows in our spreadsheet last time. Today, we're going to have different rows in our spreadsheet, but it's not going to be for that same reason. We're going to have different rows in our spreadsheet because we've got an iteration. It's for the same, we're going to be going from 1 to 2 in a single step. We're not going to be breaking that curve up into lots of different steps, but we're going to be making different guesses, and our old guesses will still be on screen because our new guess depends on the old guess. And so I wanted to emphasize the difference between a converging solution with a solution that has lots of different pieces, like we did on Tuesday. So here's our first example that's going to illustrate this. And I've given you a handout that depicts the full solution in this one, not just the columns that you're going to need, but it's got the solution, the equations, and the problem itself. So you can see that we have a section at 1, we know the depth. And we call that section 1 because that's where we know the depth. Section 2 is rectangular. We don't know the depth there, but we know that it is 7 feet above the datum, whereas the downstream section was 5 feet above the datum. So section 2, which is upstream, is 2 feet higher above the datum, and they're 1,000 feet apart. So what we're going to want to do is calculate what is the depth at 2 according to the process that was outlined in the previous slides. And what I'll do right now is pause for a few minutes so that you can put all of these columns in, but don't start filling in any numbers yet. We'll go through the equations together for the solution, and then hopefully we'll have enough time. And I've got another example that is in SI units, so you can get a feel for how things are slightly different when you're working with SI. All right, so I'll pipe down for a few minutes so you can fill in those different columns. Okay, so let's begin going through this spreadsheet process together. And the first thing we need to do is fill in some of the information for the known section that simply isn't going to change. We know, for instance, that the depth at 1 is 5 feet. That's given here in our view of section 1. We know that the area can be calculated for a trapezoid. That is the depth of 5 times the 25-foot width. Well, instead of keying it in, I'll multiply it by, oh, I must not have it written in there. Okay, 25 plus, then the sides are going to be 5 tall and 10 wide, so plus 5 times 10. So that gives me an area of 175 square feet. For the velocity, that's going to be the flow rate, Q. I'm going to anchor that, divided by the area. The wetted perimeter, again, is going to be just any place where the water is in contact with the outside edge of the channel, but not the top where the water is in contact with the air. So the wetted perimeter formula is going to be the channel width B of 25 meters. So 25 plus 2 times the square root of, so to get this length, it's the square root of the depth 5 squared plus the top width of 10 squared. So the square root of 5 squared plus 10 squared. Okay. So that gives me the wetted perimeter. The hydraulic radius is the area divided by the wetted perimeter. The energy at 1 is going to be, you can see here from the formula for energy, it's the depth, the elevation above the datum, and the velocity head. So we'll put those 3 components into the energy at 1. It's the depth, the elevation above the datum, Z1, anchoring that, and then the velocity head. So V squared divided by 2G. Since we're working with BG units, British gravitational, we have to use 32.2 for G, since it's 32.2 feet per second squared. So then we've got the energy at 1, and the slope of the energy grade line at 1 is based on, using Manning's equation, I'll drag it down here just so it's easier to view as I type it in. It is the n value times Q divided by 1.49, and that's what we have for traditional units. That 1.49 factor doesn't apply in SI units. Times the area times the hydraulic radius to the 2/3 power, and then all of that is squared. So here we've got the equation for the slope of the energy grade line. It's just having rearranged Manning's equation to solve for S. We've got the slope of the energy grade line. Now, this is going to be the same for all of the different iterations we're going to do. And you don't necessarily know at the beginning of the problem how many rows you have to have. But I think the number of rows that are pictured here, let's see, 2, 3, 4, 5, 6, 7, 8, that's going to be plenty. We should be having the same depth for all of them, though, because conditions aren't going to change at the known section. It's going to stay 5 feet because we know the depth is 5 feet there. So all of these values are going to be same throughout. Any questions so far on entering the data in for the known section? Let me pause for a minute to let you catch up. So we entered the known depth. Based on that, calculated the cross-sectional area for section 1. The velocity was Q divided by A. The wetted perimeter was the base width and the length of both of the sides on the trapezoid. The hydraulic radius is area divided by wetted perimeter. Energy is simply this formula here. It is the Z1 plus Y1 plus velocity head based on this velocity. And then we calculated the slope of the energy grade line at 1 using Manning's equation and the geometric parameters for the section there. So the area that we just calculated, the hydraulic radius we just calculated, and the known n value and q that's provided in the problem statement. So that's a brief run through on how we prepare the information needed for the known section. Okay, the next thing we have to do is just assume some depth at y2. And I mentioned before that a safe assumption generally is what if the depth is 5. Okay, now what we're going to do is calculate all of these same parameters, but based on characteristics of section 2. And section 2 is rectangular, so for area it's just going to simply be equals 25, which is this width, times whatever depth we've got. The velocity will be the flow rate divided by the area. And I need to anchor the flow rate so that any reference up to there stays into the same cell. The wetted perimeter is going to be whatever the depth is times 2, since there are two sides of it, plus 25-foot width. So 25 plus 2 times the depth, whatever that might be, just referring to the cell location. The hydraulic radius is the cross-sectional area divided by the wetted perimeter. And now the energy at 2 is the same formula as the energy at 1, but just referring to whatever the characteristics are at location 2. And so we know we have to include the depth above, the distance between the datum and the channel bottom. And I'm going to anchor that reference because it's not changing. The channel at section 2 is 7 feet above the datum and will be regardless of what I guess for the depth. Plus the depth, that's the second component of the energy, plus the velocity head. So that is v squared divided by 2g. Okay, that gave me the energy at 2. And now I'm going to calculate what is the slope of the energy grade line at 2 based on this guess of the depth. Okay, so writing Manning's equation for the known n, the known flow rate, and then 1.49 times the area that's dependent on whatever this guess of depth is, times the hydraulic radius to the power of 0.6667, 2/3 power. And then all of that is squared. So that gives us Manning's equation. We'll solve for the slope of the energy grade line just at section 2. Okay. Any questions on this next set of calculations here? I'll pause for a moment to give you a time to catch up. Okay, the formula for observed head loss, as it's shown here at the top, is just E2 minus E1. So we have E2 minus E1, and get the observed head loss. Now SF bar is just the average of the two energy grade line slopes that we've already calculated. So it is the slope of the energy grade line at 1 plus the slope of the energy grade line at 2 divided by 2. That gives us this S sub F bar. That's right. Now the head loss calculated, we're going to use this formula for the calculated head loss. Okay. So we're going to use the average energy grade line slope, it's the slope at the midpoint between 1 and 2, and multiply it by the length between them, and then also combine the C value times the difference in velocity heads. Okay, so the calculated head loss will be this slope times the length between the two is 1,000 feet. I'm anchoring that because as I drag it down later on, I want it to always refer to the same length. And then also need to add the C value that I'm given here is 0.3 for the transition, anchoring that so it'll always stay the same, times the absolute value, so ABS is the absolute value function, and I want to have the difference in the velocity heads. So the velocity at 2 is here, so V2 squared divided by 2g, 2 times 32.2, and then minus V1, so there's V1 squared divided by 2 times 32.2. Okay, I'll leave that up for a minute just so you can see it. Oh, and I need to close out the parentheses that was for the absolute value. So let's resume this. We need to now calculate the water surface at 2. And the formula I'm going to use for that, if I just put this other one away, to calculate the water surface at 2, it's going to be the water surface at 1. And remember, the definition of water surface is the Z and the depth. So I'll just combine them those two together. So it's the Z1, anchoring that, plus the depth at 1. Okay, so that gives me the water surface at 1. And now I'm going to add the velocity head at 1. So velocity head is v squared divided by 2g. Okay. Plus the calculated head loss. So now I have to put in the head loss calculated, which is cell S30. I'm having the same problem as I did last time, where since the cell is centered, my formula is starting to get into the way of where I'd want to click. So I'll just type in S30 to get the calculated head loss, and then subtract the velocity head at 2. So minus V squared divided by 2 times 32.2. Alright, that gives me the estimated water surface at 2 dependent on our guess information that we've had so far. That was our calculated water surface at 2. Finally, let me move this water surface formula out of the way, and we'll do the updated. Okay, so to get the updated water surface calculation, we have to average what we just calculated with the previous estimate. So our first estimate of the water surface at 2 was that it was going to be 7 plus the 5 depth. So our previous calculation, WS previous, is our first guess of 5 feet deep equals, okay, it was the depth of 5 plus this initial guess of the known Z2 of 7. That is WS previous. And then I also want to add water surface calculated, and then divide that by 2. So water surface previous was just based on this initial information of my assumption that it's 5 feet deep and that the channel bottom is 7 feet above the datum. And then water surface calculated, the second component of the average, is what I had just calculated here. And then percent difference is assuming that this updated value is correct. We want to find the difference between the two. So updated minus calculated divided by updated times 100. And that tells me that my initial guess was 23.8% that the new one is 23.8% smaller than my initial guess. So the difference between the new corrected, updated water surface elevation and the old one. Yeah, the difference is the updated minus the calculated divided by the updated times 100. All right, so the investment in time is just getting all of this filled in, because from there things get a little bit easier. Instead of having to guess another depth, what we're going to use as our initial depth here is going to be based on the updated. Remember, this updated water surface includes, water surface is both the elevation above the datum and the depth. And so we're going to say that the new depth should be this updated minus, we know that it's going to stay 7 feet up there for the Z2. So we'll have a new guess depth of 8.74 feet. So it's this updated water surface elevation minus the datum distance of 7 feet. And that gives us the depth of the water. Besides that, we can just drag everything down, and the numbers take care of themselves. So you highlight all of these, and you drag it down once, and you see that it's converging relatively quickly. We went from 24% difference between the input and the output value to 3% difference between the input and the output value. And if must be an error someplace. So if I drag that down again several times, it's going to automatically, for this next row, look at the previous water surface update minus the 7-foot differential between the datum and the invert. And you can see that it's getting closer and closer to convergence, and so we have a final elevation of the water surface at 2, and what it was asking, our final answer, was how deep is the water at section 2. And here we can see that the water depth is 8.05 feet. That's the actual depth of the water at location 2. All right. So what I'm going to do, we've only got 5 minutes till we need to finish for class. I'm going to hand out this other example that we didn't have time to work together. You can use it as a reference in case that's useful to you for traditional units, and also in this other example it shows how you would handle what if you had a circular section downstream and a triangular section upstream. So this one's a little bit different. I'll give you this just as a reference, but I'll circulate around and try and help you troubleshoot if you're having errors with your spreadsheet. So before I do that and finish the recording, just remember that the homework assignment is due on Tuesday, homework 13. I'll get that from you at the beginning of class on Tuesday, and also next week I'm going to give you some more information about the final exam.